in this session, as I mentioned last time, we will start talking about the Smith chart. The Smith chart is actually one of the most widely utilized tools in RF engineering, if not the most widely utilized tool. It was actually invented by Mr. Smith, Philip Hagar Smith. And in fact, I have with me here the book that he published. This is Philip Smith himself, 1969. He actually invented the Smith chart in 1939 when he was at Bell Labs. And for those of you who are on campus, you're welcome to actually come to my office and actually read the descriptions of the Smith chart by the inventor himself. It's actually been quite enlightening for me. It's quite interesting to see his enthusiasm as he actually describes different versions of the Smith chart and the different ways of utilizing that. So I don't think I can convey the same enthusiasm when I'm describing this, but I'll try my best. So the first thing I'd like to say about the Smith chart is that it does basically do what humanity has been doing for a very long time, when we have essentially been creating graphical tools to represent mathematical equations. This example that I have here is actually talking about how we have always known the rules for spherical geometry. People have been using those rules for navigation and astronomy. And specifically for navigation, we have been using them for over 20 centuries. But yet, we have been relying on graphical tools like the one you see here on the right, which is essentially the Renaissance version of a very, very popular navigation tool. And the reason we do that is because we human beings like seeing things and not necessarily in a math form. And not only this, but as people utilize those tools, they actually build intuition, meaning they build essentially memory. They know what to do when something changes and they have to make a decision very quickly. It's really the same thing that happens with the Smith chart in the RF engineering domain. So even though the Smith chart looks a little bit intimidating, and the Smith chart is actually shown right here, there's a simple version on the left-hand side and the more complete version on the right-hand side. So when you actually first look at this chart, you will probably find yourselves wondering what is really going on here. And so we're going to unravel that mystery, and once you realize what's being plotted, I think you will enjoy actually using it. In fact, it's not just that we enjoy using the Smith chart. People literally think in terms of the Smith chart. It's quite common to hear RF engineers saying, how would this change on the Smith chart? Or show me this on the Smith chart. It's really hard a lot of times to actually understand what's going on unless you can actually put your thoughts on the Smith chart. So even though today we have incredibly powerful numerical tools and we're not using the Smith chart for graphical calculations, which was the original intent, we still use it in terms of thinking and in terms of intuition building. So first of all, I want to go through a few details, and I won't go through the entire derivation, but I want to go through a few details in terms of how this Smith chart that we just saw has actually been constructed. So the Smith chart is actually trying to do something very simple, is literally trying to plot for you this equation. And even though this equation looks very, very simple, it gets slightly more complicated once you realize that both gamma L, which is the reflection coefficient of the load, as well as the ZL, which is the load itself, are actually complex numbers. So if they basically were real numbers, we would be down to the simplicity of Ohm's law, and literally nobody is creating a graphical tool for Ohm's law. But when you have a complex number, then actually that is needed. So what we actually plot on the Smith chart, basically the Smith chart is the complex plane of gamma L. So if I go back to the graph that I showed you before, the first thing I want you to realize is that this is essentially something plotted on top of gamma L. This point here, which is right next to the number 1, is actually the origin. This is the real axis of gamma L. And this is the imaginary axis of gamma L. So literally, the Smith chart is something plotted on top of the complex plane of gamma L. So if you ever get confused of what's going on, that's the first thing that you need to remember. The origin, the real axis, and the imaginary axis is essentially the plane that you see. And that nomogram is actually plotted on top. Now, we also utilize the Smith chart by essentially normalizing our impedances to the characteristic impedance of our system, Z0. Often this is the characteristic impedance of a transmission line, but even if there is no transmission line in the system, we always assume some type of a characteristic impedance. Often this is the 50 ohm impedance, which is quite common in RF engineering. And so the most common value that you will see there for Z0 is 50 ohms. So when you divide ZL by Z0, you will get this little ZL, and by this little ZL, essentially we mean the normalized impedance of the load. So the second thing I would like you to remember about the Smith chart is that when we utilize the Smith chart to link reflection coefficients to loads, we're not reading absolute loads, we're actually reading normalized loads. So again, the second lesson is that you're reading some loads because we're plotting the equation between gamma L and ZL, but we're reading normalized loads. So if I take now this equation that I just wrote here, and I basically explicitly write that gamma has a real part and an imaginary part, and that my normalized ZL also has a real part, little RL, and an imaginary part, little XL, I can essentially now go ahead and separate real and imaginary parts. So if I go ahead and do all the math, and I separate now, here is again my normalized ZL, and this is the real part of gamma, and this is the imaginary part of gamma. So if I go ahead now and I separate my real and imaginary parts, I will get with two algebraic equations. Here's the first one, and here's the second one. And the beautiful thing is that each of these algebraic equations actually links only one parameter of R and X. So you can see, for example, that the first equation includes only RL, while the second equation includes only XL. And for those of you who might remember well analytical geometry, you will find out that each one of these equations actually represents a circle. So this is a circle, and this is a circle. So if we actually were to plot these, we would end up with two families of basically a bunch of circles. The first one would be a family of circles that represent different values of real part of the load. So again, this is the real part of ZL. And the second family would represent circles that are essentially linked to the imaginary part of the load, the little XL. So literally, the nomogram that you saw before is really those families of circles.